What are free body diagrams? How are they used? Today, we'll explore how to take the physical forces acting on an object and represent them visually and mathematically, making complex problems easier to solve. This foundation will help you understand how to break down real-world situations into clear, manageable models that reveal the underlying physics. Let's get started. Next, we focus on the object itself by defining our system of interest. In this case, we simplify the crate by representing it as a single particle with mass placed at the origin of our coordinate axes. By doing this, we remove the person and the floor from the analysis, allowing us to concentrate solely on the crate's motion and forces acting on it. This approach makes the problem easier to handle mathematically while preserving the essential elements we need to study. Now, we add the weight vector to represent the force that gravity exerts on the crate. This force acts downward because Earth's gravity pulls the crate's mass toward the ground. The weight vector points straight down along the y-axis. It's calculated by multiplying the mass of the crate by the acceleration due to gravity, which is 9.8 meters per second squared. This step is important because it shows how gravity affects the crate in our analysis. Now we add the normal force, which is the floor's reaction to the crate's weight. This force pushes straight up, perpendicular to the surface. Since the crate isn't moving up or down, the normal force must be equal in size to the weight pulling down. That means these two forces balance each other perfectly, so the crate stays still vertically. Now we add the applied force, which is the force the person exerts on the crate by pushing it forward. This force acts horizontally and is represented by the arrow pointing to the right. Alongside this, we still have the normal force pushing upward and the weight pulling downward due to gravity. The applied force is what causes the crate to move forward, and it interacts with the other forces acting on the crate. This step is crucial for understanding how the crate starts to accelerate when pushed. Now we introduce friction into the situation. The rough concrete floor applies a kinetic frictional force that acts opposite to the crate's direction of motion. In the diagram, you can see this frictional force pointing to the left, countering the applied force on the right. The normal force acts upward, balancing the weight of the crate, which points downward. Notice that the frictional force vector is drawn shorter than the applied force vector, reflecting that the crate is still accelerating forward despite the friction opposing it. This shows how friction slows the crate down but doesn't completely stop its movement in this case. At this stage, we see that the vertical forces are completely balanced, which means there is no net force acting up or down. However, the horizontal forces don't balance out. The applied force pushes to the right, while the frictional force opposes it to the left. Since these forces aren't equal, their vector sum results in a net force directed towards the right. This net force is what causes the object to accelerate along the horizontal axis. Understanding this helps us see how the object's motion is influenced by the interplay between applied force and friction. Now that we have the free body diagram set up, the next step is to break down the forces into their x and y components so we can use Newton's second law in algebraic form. Along the y-axis, we look at equilibrium where the normal force balances the weight, so the net force is 0 and the normal force equals mg. On the x-axis, we consider the dynamic forces, where the applied force pushes forward and the kinetic friction opposes it. The net force here equals mass times acceleration along x, which is the difference between the applied force and friction. This setup allows us to solve for acceleration or forces systematically. Here, we focus on mapping only the external forces acting on each skater. The key point is to include forces that come from outside the system, which means we should never show both forces from an action-reaction pair or internal forces between parts of the system. In the example, the correct way is to show just the force that skater 2 exerts on skater 1, not the force skater 1 exerts back on skater 2, since those two forces act on different bodies and are an action-reaction pair. Including both would be incorrect because it mixes forces acting on different objects. Following this rule helps us clearly understand how external forces influence each object independently. When dealing with forces that aren't aligned perfectly along one axis, we break them down into perpendicular components to make calculations easier. By using trigonometry, we resolve a force into its horizontal and vertical parts, which are called orthogonal components. This process allows us to work with the separate x and y components instead of the force as a whole. Specifically, the horizontal component is found by multiplying the force by the cosine of the angle it makes with the horizontal axis, and the vertical component is found by multiplying the force by the sine of that angle. These components are then what we use in our algebraic equations to analyze the system. Now let's look at the squiggly line technique. When you break a vector into its horizontal and vertical parts, the original vector isn't really acting anymore. It's just the sum of those parts. To make this clear, you cross out the original vector by drawing a squiggly line over it. This shows that it's been fully replaced by the components along the x and y directions, so you don't accidentally count it twice. This little step helps avoid mistakes and keeps everything clear when working with forces. Now, let's focus on how Newton's second law applies when we break forces down along different directions. The total force acting on an object is equal to the mass times its acceleration. But since forces and accelerations are vectors, we can separate this into components along the x-axis and y-axis. By summing all the forces in the x direction and setting that equal to mass times acceleration in the x direction, and doing the same for the y direction, we can analyze motion more clearly. This approach helps us organize the problem so that we can independently find how forces influence motion along each axis, making it easier to solve for the overall movement. At this point, it's important to understand that no matter how complex a physical situation might seem, there's a straightforward process we can follow every time. It involves 4 key steps. First, we identify the system by sketching out the physical setup. Then, we isolate the system and draw the external forces acting on it using a dot and vector map. Next, we resolve those vectors into horizontal and vertical components so we can analyze them more easily. And finally, we apply the laws by writing equations that sum the forces in both the x and y directions. By turning the real-world problem into this structured free body diagram, we make sure we're setting up the right equations to find the correct solution. In this scenario, we're looking at a crate being pulled across a rough horizontal floor by a rope, which creates a classic dynamics problem. Our main objective is to find the crate's horizontal acceleration. Several forces are at work here. The rope's tension pulling the crate at an angle, the crate's weight acting downward due to gravity, a normal force pushing upward from the floor, and kinetic friction that resists the motion. Understanding how these forces interact will help us set up the equations needed to calculate the crate's acceleration. Let's look at this scenario where the crate stays on the floor, so there's no vertical acceleration. This means the acceleration in the y direction is 0. The forces in the horizontal direction, however, are what cause acceleration. Vertically, the crate is in equilibrium, meaning the normal force plus the vertical component of tension equals the weight of the crate. Horizontally, the net force is the horizontal component of tension minus the kinetic friction force, and this net force causes the crate's acceleration along the x-axis. This way, we clearly separate the forces acting to keep the crate in place vertically and the forces that make it accelerate horizontally. Let's begin by considering a simple scenario where a mass is resting on a rough, inclined surface. The surface is angled at some angle theta, and the mass is subject to forces due to gravity, friction, and the normal contact with the surface. To understand how this mass will move or stay in place, it's crucial to isolate it from its surroundings and represent all the forces acting on it clearly. This process helps us create a free body diagram, which shows just the object and the forces involved without any distractions. This simplified view lets us analyze the motion or equilibrium more effectively by breaking down the problem into manageable parts. Next, we adjust our coordinate system to match the inclined plane's angle. By tilting the axes, we set the x-axis to run parallel to the surface, while the y-axis is perpendicular to it. This makes it easier to analyze motion along and normal to the plane, as all forces and displacements align with these new directions. Setting up the axes this way is a key step in simplifying the problem. Now, let's focus on how weight, or gravitational force, acts on the block on this inclined plane. Weight always points straight down toward the center of the Earth, no matter the surface angle beneath it. Here, we show the weight vector as pointing vertically downward, with a magnitude equal to mass times gravitational acceleration. Because the plane is tilted at an angle theta, this weight vector forms the same angle theta with the negative y-axis we defined to be perpendicular to the surface. Understanding this setup lets us break down the weight force into components parallel and perpendicular to the incline, which is essential for analyzing the block's motion and forces acting on it. This step lays the groundwork for the next stages of solving the physics of the inclined plane. Here, we break down the weight of the block into two parts that match the directions we're focusing on. One part of the weight pushes the block directly into the surface of the incline, which is represented by mg cos theta. The other part pulls the block downward along the slope of the incline, shown as mg sin theta. This helps us better understand and analyze the forces acting on the block in terms of the incline's angle and orientation. Now that we've outlined the forces acting on the object on the inclined plane, let's focus on the normal force. This force is the surface pushing back up, perpendicular to the plane, supporting the object's weight. Since the object isn't accelerating vertically, the normal force exactly cancels out the component of gravity acting perpendicular to the surface. We calculate it by multiplying the object's weight by the cosine of the incline angle. This balance keeps the object from sinking into the plane or lifting off. Now, we introduce friction, which is a force that always works against the motion of the object. It acts along the surface in contact parallel to the plane. In this case, friction opposes the block sliding down the incline. The force of friction points up the slope, counteracting the component of the block's weight that pulls it downward. This force depends on the nature of the surfaces in contact and plays a crucial role in determining whether the block will move or stay at rest. Next, we'll look at how this blueprint brings everything together into a unified view of motion. By breaking down the forces acting on the body into perpendicular and parallel components relative to the slope, we simplify the problem considerably. The forces perpendicular to the slope balance each other out, putting us in static equilibrium, as shown by the equation where the normal force minus the component of gravity perpendicular to the surface equals 0. Meanwhile, the forces parallel to the slope combine to create acceleration, captured by the dynamic equation where the component of gravity along the slope minus friction equals mass times acceleration. This separation transforms what initially seems like a complex motion problem into straightforward algebra, making analysis more efficient and easier to understand. In this scenario, we're looking at two blocks connected by a string over a pulley, creating what we call a coupled system. Even though the blocks are moving in different directions, one up an incline and the other vertically downward, they are linked in such a way that they share the same magnitude of acceleration and tension in the string. This means that when block A moves up the slope with acceleration A, block B moves downward with the same acceleration. Similarly, the tension throughout the string is uniform, so both blocks experience the same tension force denoted as T. Understanding these shared constraints helps us analyze the motion of the system as a whole and solve for unknown forces or accelerations. Let's review the key concept for handling this type of problem. We need to draw separate free body diagrams for each object involved, making sure not to combine them into one. In this system, the tension T in the connecting medium and the acceleration A serve as mathematical links between the two objects' individual equations. On the left side, for the first object, we see forces including tension T, the normal force N, kinetic friction Fk, and components of gravitational force split along the inclined plane by angles involving theta. The sum of forces along the x-axis equals the tension minus the component of weight along the incline and friction, which equals mass times acceleration. On the right, the second object has tension T acting upward and weight acting downward, and the sum of forces along the vertical axis shows the difference between weight and tension equals mass times acceleration. By analyzing each object separately but connected through tension and acceleration, we set up two equations that can be solved together to find the unknowns in the system. To summarize, free body diagrams are essential for understanding classical mechanics because they help us translate real-world physical situations into clear mathematical expressions. By isolating the object and identifying all the forces acting on it, then breaking these forces into their components, we create a roadmap to apply Newton's second law with confidence. This process bridges the gap between what we observe and the precise calculations that describe how objects will move. It's a straightforward method that reduces complexity and lets the physics guide us to the solution.